One of the most important results to come out of cosmology and observations of the cosmic microwave background has been that by redshift of approximately 6, most of the universe has been fully reionized following the formation of the first galaxies and stars. It's unclear currently what the source of those ionizing photons were. Recent work suggests that low luminosity star-forming regions could have supplied a dominant number of ionizing photons to the universe's reionization. However, these results depend heavily on the fraction of ionizing photons which escape star-forming regions and galaxies on whole. If that fraction is low, say 10%, then there still is uncertainty in whether the observed galaxies could have reionized the universe. However, if that fraction were, say, be 50%, then the number of ionizing photons produced and entering the intergalactic medium by small star-forming galaxies would be capable of reionizing the universe. However, the amount of ionizing radiation which escapes a star-forming region, let alone an entire galaxy, is very uncertain. Take, for example, M17, a Milky Way star-forming region. Peering through the gas and dust, we see that this region houses dozens of O and B stars, which produce an intense amount of ionizing UV radiation, the same type of radiation responsible for the reionization of the universe. However, that same gas and dust which formed the stars and now obscures our view also absorbs the ionizing radiation, making the escape fraction from this object probably quite low. Before going any further, let's do a quick review of star-forming regions and the structure of ionized gas surrounding them. In an idealized spherical star-forming region, the ionizing radiation from a massive star will produce a zone dominated by ionized hydrogen, doubly ionized oxygen, and doubly ionized sulfur. As the radiation field internally drops due to geometric dilution and the absorption of radiation by gas and dust, the ionization state of the gas becomes dominated by singly ionized sulfur, nitrogen, and oxygen. This marks the boundary between neutral gas and ionized gas. And thus, using the projected surface brightnesses of that singly ionized sulfur to the doubly ionized oxygen, we can form diagnostics of low optical depth, indicated by the left-hand column of our models, to high optical depth, indicated by the right-hand column, which shows a region dominated by singly ionized sulfur. Thus, the ratio of singly ionized to doubly ionized sulfur and oxygen allows us to diagnose high escape fractions in nearby star-forming regions. With an understanding of how the ratio of singly ionized sulfur to doubly ionized oxygen emission can be used to trace the presence of ionization fronts and the escape fraction of ionizing radiation from nebula, we turn to ionization parameter mapping on galaxy-wide scales. The first application of ionization parameter mapping, using the ratio of singly ionized sulfur to doubly ionized oxygen, from here on referred to in spectroscopic notation as sulfur 2 to oxygen 3, was done using the large and small Magellanic clouds. These are nearby enough that the structure of individual star-forming regions can be resolved, allowing us to identify the presence or lack of an ionization front. We use emission line data from the Magellanic Cloud Emission Line Survey. Taking the ratio of sulfur 2 to oxygen 3, highly ionized regions are now visible as black structures. Surrounding many black structures, such as NGC 2030, is a region of white emission. This indicates a high ratio of sulfur 2 to oxygen 3 surrounding the highly ionized gas in the center. This indicates an ionization front and a low escape fraction of ionizing radiation. However, regions like 30 Doradus, the most massive star-forming region in either the large or small Magellanic Cloud, often lack a defined ionization front, indicating a high escape fraction. Before we can estimate the escape fraction from an entire galaxy, we must estimate the escape fraction from all of the individual star-forming regions. On the left, DEM S38 is an example of an optically thick star-forming region. Its morphology with a solid transition from oxygen 3 to sulfur 2 indicates the presence of an ionization front. To these objects, we assign an escape fraction equal to 0%. Star-forming regions, similar to the one in the lower left, have a very irregular morphology. Our model suggests that the escape fraction from regions such as this may be as high as 60%. Blister regions on the right-hand side are a hybrid scenario. For these, we have the escape fraction from the irregular objects and leave our escape fraction at 30% for the remainder of our analysis. As an example of how these compare to our models, we re-show the projected sulfur 2 to oxygen 3 ratios. Why did I stop? In order to use H alpha to trace the ionizing luminosity of the stars, we must correct for the fraction of ionizing photons which will never encounter gas and never produce an H alpha photon. We use the following equation once we have assigned an escape fraction to a nebula to determine its intrinsic ionizing luminosity. Ionization parameter mapping has given us a surface brightness independent census of all star-forming regions in the large and small Magellanic Cloud, and has also allowed us to estimate the escape fraction of ionizing radiation from these regions individually. We find an H alpha transition luminosity of 10 to the 37 ergs per second, above which the H2 regions become dominated by optically thin objects. These will contribute most of the ionizing radiation into the galaxy. An average escape fraction in that large Magellanic Cloud for the H2 regions is 42% and 40% for the small Magellanic Cloud. We also estimate the escape fraction of ionizing radiation from the galaxy as a whole. In the large Magellanic Cloud, we find this to be 11 to 17%, and in the small Magellanic Cloud, 4 to 9%. We also compared the distribution of optically thin and optically thick regions with projected H1 column. As expected, higher neutral hydrogen columns, it correlates better with high optical depth objects in both galaxies. There is a difference between galaxies, which is attributed to projection effects causing a higher H1 column to be observed. Ionization parameter mapping has given us a surface brightness independent census of all star-forming regions in the large and small Magellanic Cloud, and has also allowed us to estimate the escape fraction of ionizing radiation from these regions individually. We find an H alpha transition luminosity of 10 to the 37 ergs per second, above which the H2 regions become dominated by optically thin objects. These will contribute most of the ionizing radiation into the galaxy. An average escape fraction in that large Magellanic Cloud for the H2 regions is 42% and 40% for the small Magellanic Cloud. We also estimate the escape fraction of ionizing radiation from the galaxy as a whole. In the large Magellanic Cloud, we find this to be 11 to 17%, and in the small Magellanic Cloud, 4 to 9%. We also compared the distribution of optically thin and optically thick regions with projected H1 column. As expected, higher neutral hydrogen columns, it correlates better with high optical depth objects in both galaxies. There is a difference between galaxies, which is attributed to projection effects causing a higher H1 column to be observed. I have completed ionization parameter mapping using the sulfur-2 to oxygen-3 optical line ratios. This has allowed us to create the first of its kind catalog of all star-forming objects in a galaxy, using only the ionization structure to define the borders between neighboring objects. We have also been able to estimate the escape fraction of all star-forming regions as a function of H-alpha luminosity and for the star-forming galaxies as a whole. Additional observations of M33 have been completed to allow us to continue this research in another galaxy with higher metallicity and higher star formation rate. We have also included oxygen-2 as an important way to break the remaining degeneracy between stellar effective temperature and H2 region optical depth. Thank you.